All right, welcome to the deep dive on what's new with Databricks machine learning. If you've seen the keynote earlier today, you've already seen the exciting new announcements that we've made. In this talk, we'll have much more time to dive into each one of the components of Databricks machine learning, and I'll also cover the new components that we announced earlier today. This is the overview of Databricks machine learning, a data-native and collaborative solution for the full machine learning lifecycle. So I'm going to be walking through each one of these boxes and talk about what we cover in these boxes, what functionality is available, and some roadmap items of what's coming in the future. As mentioned, AutoML and the feature store are two brand new components that we're adding today. Now, before we go through each one of these boxes, let me cover off how you get actually access to Databricks machine learning. We've added a brand new persona-based navigation to Databricks, where you can select between data science and engineering, machine learning, and SQL analytics. This gives you access to a purpose-built surface for each member of the data team. If you care about machine learning, you can configure the navigation to be in the machine learning configuration to have access to the specific components. But if you don't care about machine learning and if you're a SQL analyst, you can click on SQL Analytics and you have a purpose-built surface only for that purpose. But if you are in the Databricks machine learning configuration, this new dashboard gives you access to all of the machine learning related assets and resources, like the most recently viewed feature tables, models, or experiments, and entry points to our new AutoML product as well. So coming back to this overview, and let's start with data, which is the most important piece of any machine learning platform. Of course, Databricks machine learning is built on an open data lake foundation with Delta Lake. Now that has a lot of implications of the scalability and what type of data that you can access. And really what we're talking about is this data prep and data versioning component in Databricks machine learning. So let's quickly dive into this topic. Delta Lake provides a lot of powerful capabilities for machine learning. The most important one is that it can ingest any type of data at any scale from any source. So you may imagine you have images, tabular data, audio, maybe even videos that come in from all kinds of different sources. And Delta Lake really enables you to ingest all of this data and process it at high scale. Of course, that works across cloud on all of the different data lake products that you're familiar with. And specifically for machine learning, Delta Lake provides optimized performance of reading from and writing to Delta tables. And because Delta provides ACID transaction guarantees, you can be sure that your data for machine learning are always available at consistent quality, so that you can train on high quality data and don't waste training time on data that doesn't conform to your expectations. And then you'll see later as well, we have integrated Delta with MLflow, and specifically we use the Delta data versioning feature that is used to provide time travel to actually provide you with full lineage and governance in MLflow. So when you train a model and log the information to MLflow, we track exactly which Delta table you use and which version of the Delta table that you use, which comes in handy for reproducibility. So jumping out of the data aspect to the data science workspace that makes Databricks machine learning collaborative. One of the most important parts of building a product for every member of the data team is providing multi-language support. Databricks notebooks provide support for Scala, SQL, Python, and R, all within the same notebook. So your first cell in the notebook can be a SQL query to load data, and the next one can be Python to train a machine learning model. Now, this multi-language support really comes into play when you can actually collaborate with multiple people. So Databricks notebooks can be shared within a data team and provide cloud-native collaboration features such as commenting, co-presence, and co-editing. So you can really in real time collaborate with your colleagues. And finally, and most importantly, MLflow experiment tracking is deeply integrated with the Databricks notebook product. So there's an experiment sidebar that shows you the latest runs that have been tracked from this notebook, all of the parameters, metrics, and models. And it's also integrated with code versioning from the notebook. So each time you create an MLflow run from a Databricks notebook, we snapshot the version of the code, and which is used later for reproducibility. And of course, during experimentation, you can iterate fast on your code, but for production workloads, ideally you want to check it into Git repositories. So we provide a native integration through our new repos feature with the most popular Git providers. that allows you to check in the code into your Git repository and pull changes from Git and integrate it with your CI/CD systems. So from the data science workspace, let's go to the core of Databricks machine learning, where you can train your models. At the center of this platform is really the machine learning runtime that provides a DevOps-free environment for optimized machine learning. In this screenshot here, you can see configuring a Databricks cluster to use the GPU runtime, which actually has all of the GPU drivers pre-installed and pre-configured so that you can utilize GPUs to train your machine learning models. The machine learning runtime packages up all of the most popular machine learning toolkits and make sure that they're well tested and can run at scale. So we include TensorFlow, Keras, PyTorch, Scikit-learn, XGBoost, and a much, much longer list of the most popular frameworks. You can just use the machine learning runtime and get going without worrying about setting up your environment. Of course, we support distributed machine learning natively, so we also package up a popular library called Horovod that allows you to distribute your TensorFlow and PyTorch models. And finally, we also integrate with popular hyperparameter tuning libraries such as HyperOpt that is natively built into the machine learning runtime. And the machine learning runtime also contains our new AutoML product that we announced today. So let's jump into the AutoML product and cover it in more detail. When we look at AutoML, we really see there's an opaque box that often leads to a lot of different problems. The way that we frame this is that there's a lot of different people that do machine learning at different levels of familiarity with machine learning libraries. ML experts and AI researchers really want full flexibility. And we like to use a driving analogy for this. Really what they want is a manual transmission, 3 pedals and a gear shifter. One developer engineers that may not be formally trained in machine learning, but can still do data science into machine learning models. And they just want to have the most tedious things taken care of for them. So the analogy in driving is an automated gearbox, so that they don't have to worry about shifting and which gear they're in. And last but not least, our citizen data scientists, where there's a promise of full automation. And the reason why I like this analogy is that fully autonomous cars just don't quite work yet. And you know that they work really well in really constrained environments, but once they get out of their depth, and if there's no controls so that you can take over, all you can do is open a door and leave. And that's what we see happen with a lot of the products that are targeted at this like fully autonomous level in data science and machine learning, that they work really well in demos and POCs, but then you reach their limits and there's no way out. So we basically approach AutoML in a very different way. So our AutoML product is embedded in our experiment management product, and there's also different entry points. But the default entry point will be the creation of a new experiment. And then there's a UI-based workflow that takes you through configuring your AutoML run, augmenting your data with different tables from the feature store, which I'll discuss later, training and evaluating these models and deploying them, all within the UI. Now, this addresses this fully autonomous UI only level. However, if you want more flexibility, or if you have an expert that you're collaborating with, our AutoML product generates an MLflow experiment and runs in this experiment to track all of information. And in addition, it also generates code for each one of the models that it produced. And that code is the native code that you would have written if you had written that model. So let's say the best model from the AutoML run is an XGBoost model. The notebook that is generated for this XGBoost model is native XGBoost code that loads the data, trains a model, and adds it to the model registry. And we also add things such as model interpretability to help you understand your model. So now you can actually break glass into one layer of abstraction below, look at the code and customize it, or pass it on to an expert who can apply domain knowledge to this ML framework, which provides you with this level of control within the AutoML product. So now that we talked about model training in AutoML, let's talk about the other new component, the feature store. So feature stores really solve a key problem of reusing features that are being written for machine learning models and helping with the deployment path. In this graph that was also used in the keynote, you can see how we go from raw data, apply some transformations, and then train machine learning models. The first component of the feature store is what we call the feature registry. That really takes care of tracking what feature tables you use, what features are in those feature tables and what is their schema, the upstream and downstream lineage, which I'll discuss in more detail in a minute, what code was run to produce these features, and versioning. And that is also the component that powers our UI that I'll show you on a later slide in the screenshots. Once you define your features and they're added to the feature registry, there's two different access patterns. The first one is batch for high throughput. So you can train your models directly on features from the feature store. And that is really important because once you train models directly from the feature store, we can actually retain that metadata within the model. And I'll discuss that in more detail on a later slide. But for storing the features offline and training the models, one key aspect about our feature store is that this was co-designed with Delta Lake. So the feature store really inherits all of the benefits from Delta Lake. Most importantly, that the features are stored in an open format that can be accessed through native libraries and APIs. And of course, all of the aspects about Delta Lake in terms of versioning also apply to our feature store. The second access pattern is online for low latency. And so the feature store really guarantees that the features that are read for training and for online serving are equivalent, which removes the risk of online-offline skew. And of course, if you read the features from an online store, it removes the necessity to implement these features on the client. So that already significantly simplifies the client, but the client still needs to deal with the complexity of knowing which versions of the features it needs to request from the feature store to pass to a specific version of the machine learning model. So what we have done in our feature store, and the reason why we co-designed with MLflow, is that we actually store the information about which features a model understands in the model format itself. So if you train a model using features from the feature store, the MLflow model format carries forward the information about which features came from the feature store, which versions, and how to extract them, so that in model deployment, the client can be completely oblivious to the fact that there is a feature store in the first place and just send the raw features to the model. And then the model deals with extracting or looking up the features from the feature store. Now that significantly simplifies the deployment of these machine learning models. And it also means that you can actually update features in the feature store without touching the client, which accelerates model deployment and makes it much, much easier. So this is a screenshot of the UI that is powered by the feature registry. And I just want to highlight the lineage aspects. So in the UI, you can here see that we have upstream data sources. What that means is we automatically track which data sources are used to compute a specific feature. That is not only important for lineage and governance, but also for feature reuse. So now data scientists can come to the feature store UI and find all of the feature tables that are being computed based on the raw data that they're planning to use. And this is a much better way of actually discovering features than just trying to guess a name that someone else gave the feature tables. So this is upstream lineage. We also implemented downstream lineage. So on the feature table detail page, you can see for each feature where this feature is being used. So we track exactly which models, endpoints, jobs, and notebooks are using a specific feature. Now, as you may be able to guess, that's really important so that we can actually answer the full end-to-end lineage question, such as what raw data do you have? What are the features that are being computed on those raw data? What are the models that consume these specific features and where are these models being deployed? But it also helps with answering questions such as, is it safe to deprecate a feature table? If you're planning to deprecate a feature table that still has consumers, probably you should first check on those consumers and see if it's okay to turn down those feature tables, because it will most likely break those consumers that rely on these features. So now that we went from model training and how we can make sure that the features are available at training and online, let's look at the different deployment options. So the Databricks machine learning provides a model registry based on the MLflow model registry out of the box. And of course, through using the MLflow model format, we have all of the model deployment options available to us because MLflow is open source. And the open source project provides a lot of different flexibility for model deployment. So as you can see, you can easily build a Docker container and deploy it on your own Kubernetes cluster. You can easily deploy MLflow models as Spark UDFs, which I'll show in a minute. There's a lot of different integrations with online inference services. And because the MLflow model just wraps up the native serialization formats, you can also, of course, pull out those formats and run them on on-device runtimes, such as Onyx and TensorFlow Lite. So let's look at two specific deployment use cases in more detail. The first one is batch scoring. So this is the line of code, or the 2 lines of code, that you have to write to apply an MLflow model as a Spark UDF. And here you can actually see that we're using the model registry. So we're requesting the production version of the model named Clemens Winfarm signature and applying it as a UDF to a Spark data frame. That's how simple it is. Now, this is the line of code that you would write if you wanted to apply an XGBoost model as a Spark UDF. This is the line of code that you would write to deploy a scikit-learn model as a Spark UDF. And this is the line of code that you would write to deploy a TensorFlow model as a Spark UDF. So just for dramatic effect, I'm going to go back. XGBoost, scikit-learn, TensorFlow. And yes, you may have noticed it. They're all the same. And this is one of the benefits of the MLflow model format, is that it has this PyFunc flavor, which abstracts away what ML framework you used and exposes them as a Python function. So in the deployment path, you don't have to worry about what ML framework was used initially. And it's extremely important because if there's many people using different ML frameworks within your company, you don't want to have to change your deployment every single time someone comes up with a new model in a new model framework. And these, of course, are just 3 examples. MLflow supports many different ML frameworks as well. And on the online serving side of the options, we do provide model serving out of the box in Databricks. It's actually one-click deployment of MLflow models. You just have to go to the model registry and click Enable Serving. And we will expose all of the active versions within that model as a REST endpoint. And here you can see a screenshot of the serving product where you can see all of the active versions being ready for serving. And of course, the serving product being integrated in the model registry knows which model versions are at which deployment stage. So if you call the production endpoint, the request will always be sent to the active version that is marked production in the model registry. So now that we've discussed all of the different components to train your models, to track your features and to deploy them, let's look at the foundation really that forms the MLOps and governance layer in Databricks machine learning. And what we've really found is that MLOps is really the combination of DataOps, DevOps, and ModelOps. And of course, on Databricks, we provide DataOps through Delta Lake and data versioning using the time travel feature, DevOps with integration with repos and Git providers, and ModelOps with model lifecycle management through MLflow. So we're going to look at each one of the components of MLflow from the model format to tracking to the model registry and the deployment options. And we're going to be looking at how we actually enable end-to-end MLOps and governance on Databricks by integrating all of these different components. And it's anchored on capability that we're building that we call autologging. What you often look at when you look at tracking your parameters and metrics in your machine learning framework is code like this, that logs all of the parameters and metrics in the model artifact itself. Of course, we can simplify this because this code starts looking awfully similar for all of the different models that are being trained. So we've introduced autologging, which provides an autolog API for all of the popular ML frameworks that takes care of all of this work for you. And with one line of code, you get all of the metrics, all of the parameters, and the model artifact logged to MLflow. And because we provide many different autologging APIs, and I'll show you later of the different things that we can automatically log, we even simplified it more so that you can just call MLflow.autolog and we will log all of the information that we can for you. So taking this MLOps and governance layer and unboxing it to look at the different components, we'll walk through DataOps, experiment tracking, DevOps, and ModelOps to show you how we actually automate the full end-to-end lifecycle. So starting with DataOps, we also automatically track what data that you access in your MLflow run. This uses the Spark Data Source API, so it actually works for every Spark data source. If you read a CSV file using the Spark Data Source, we will keep track of the name of the CSV file that you've accessed. But if you read a Delta table, we can not only tell you which Delta table you read, We can also tell you what version of the delta table that you used, because delta has a time travel feature. And this actually provides you with end-to-end governance in terms of taking a model and finding out what data you've used when you trained that model. We also capture which features the model actually takes in. Of course, this is important for the feature store to know exactly what features are being fed in, but it's also important for many different use cases, such as being able to tell whether two model versions are compatible based on their schema. And this works transparently for all different ML frameworks. So it doesn't matter if you're using TensorFlow, PyTorch, Scikit-learn, or SparkML, this schema will always be available in MLflow. This is the auto logging that I just showed you for specific to machine learning frameworks. So for all of these frameworks, we keep track of the parameters, the metrics, and the model artifact itself without you having to specify any of it. You just have to call mlflow.autolog. As mentioned earlier, in the machine learning runtime, we also package up hyperparameter tuning libraries. So if you run hyperparameter tuning on Databricks, we automatically keep track of all of the different trials and the parameters that you used. And in MLflow, we actually visualize this using this parallel coordinates plot. And again, all of this is automated and out of the box without you having to specify anything. And then we're also we're in the process of adding automated model interpretability using the Scheib library under the hood. So depending on the model type, we will give you feature importance. So here on the right side, you can see feature importance for, I believe, is a tree-based model under the hood. And on the left side, you can see if you have an image model, we can give you these plots that tell you which areas of an image contribute to the classification. In this case, it's an aircraft classification model. And then on the DevOps front, of course, we keep track of the exact code that you use when you train a model, the hardware configuration of the cluster, and the environment configuration. And you may be able to tell where this is going, and you'll see it in a couple of slides. And then on the model ops front, of course, we have the model registry that is really becoming the GitHub for machine learning models that keeps track of all of the models and their versions. And we provide stage-based access controls in the model registry to facilitate the handoff in the deployment lifecycle. So on this slide, you can see actually the stage requests and stage transitions, which again depends on your access controls. So if you don't have access to make a model production, all you can do is request a transition to production. And then someone else who has the appropriate access controls gets notified and can reject or approve your request. And we keep a full audit log of those activities, so you can basically tell when changes to your model happen and when it was made production, when it was archived again. And then, as you saw earlier, deploying a model as a REST endpoint from there is a one-click process. The model serving part, of course, is integrated with the model registry and understands the production tags and exposes your model as a REST endpoint from there. And of course, it also keeps a full audit log of what happened to the model and when it was deployed by whom. And last but not least, here's an example of a streaming model quality monitoring application that actually computes a streaming RMSE to tell you the model quality as new requests and predictions come in, and also alerts based on the quality. There's much more investment that we're going to be making in model quality monitoring in the future, but this is just one example. So finally, as you may be able to guess, the result of all of this is full end-to-end governance and reproducibility. Because once you have the code that you used, the data that you used, the cluster configuration, the environment specification, we can give you a single button that reproduces a run and gives you the exact environment that you used when you originally trained the model. So in summary, this is Databricks Machine Learning, a data-native and collaborative solution for the full machine learning lifecycle. It contains all of the different capabilities for you to go from data to model training to evaluation and deployment of these models in all different environments, with full MLOps and governance that stretches from data ops and the versioning of data to DevOps and versioning of your code, and model ops and of versioning your models and deploying them, all on an open data lakehouse foundation that is built on Delta Lake. Of course, as always, there's much more content, so please feel free to go at databricks.com/ml to learn more.